Our second speaker today is Núria Fagella, and she will tell us about quasi-conformal surgery on boundary domains. So please.
Thank you, Mario, for the introduction, and thank you, the organizers, Misha, etc., for this invitation. I'm actually happy to share this with this audience, right? We were neighbors in MSRI in 2022. That's how we kind of got to know each other. So it's very nice to be here. Okay, so I'm going to talk about a small part, or not small, I don't know, on the work with Vasiliki Evdoridou, Leticia Pardo, who is now in Barcelona, and Lucas Gaia. And this part, even if the paper which we put in the archive like last week, I think, or yeah, more or less, is about grand orbit relations and quasi-conformal deformations of functions and blah, blah, blah. There is one theorem that I think is interesting on its own, which is this quasi-conformal surgery that I'm going to explain today. Well, just in case that somebody in this audience is not dynamical, but I think that's not really the case, but just to know that we iterate functions, holomorphic maps on the plane, in this case, in the case of this talk, right? We are interested in the asymptotic behavior, so not only on the properties of the map, but precisely on the asymptotic behavior of these orbits. And you know, motivation comes from many different areas, starting from root finding algorithms, but also how useful it is in dynamics, because many times has given a lot of information about real systems, but also because of the beauty of all the areas that connect and that everybody can find their interest topic in the subject, right? So let's just remember, like Han has already used this, but remember that we have this very big partition, totally invariant, which is this partition into the Fatou set, which is this normal, is like the open set where the iterates form a normal family, so that they have limit functions, or partials have limit functions. Basically, you should think of it as every point behaves like the neighbors do, dynamically. And then that's like a big open set. And then the Julia set, which is like the boundary in between these stable, dividing these different stable regions or components, right? And that's where we have chaos, and you all know very well what this is about. So here, the outside, this is a polynomial. The red and the yellow would be exactly the stable components, because here every orbit goes to infinity locally uniformly. Here everything rotates like an irrational rotation. Any other component maps eventually to here. And then the black, which is this boundary, supports the tension between the different stable behaviors, and that's where chaos occurs. So you have repelling periodic orbits that are dense there, etc. And this is where Han was trying to put some measures, which in this case are very well understood, but in the transcendental case, as you can see, things are more messy, simply topologically more complicated, also dynamically. Well, you have a singularity, essential singularity at infinity that shoots you back every now and then, or mostly all the time. So naturally, there is more injection of chaos into the system, right? So the Fatou set, which is where we will stay today, is open, typically with infinitely many Fatou components. The boundaries are in the Julia set. So when you look at Fatou components, these connected components of the Fatou set, you basically have a dynamical system of components. So components map to components. So either you have like a cycle, this would be the periodic case, or you have a component that eventually maps into a cycle. This would be the pre-periodic case. Or the only one that is left is the wandering situation where components map forever without ever intersecting any of the previous iterates. This would be the wandering domains, which is where we will work today. But before we go into that, let me just make a quick review of the relation between of the easy case, and let me put quotes here, right? So when you have periodic Fatou components, an important tool is the inner function that they actually induce. So if you have a, let's say, period 1 component that maps to itself under a map F, if you use, let's say it's simply connected, and with this, I'm not restricting too much because since we will move in the world of entire functions, everything is basically simply connected, okay? So this is not this is what we deal with. So you can use the Riemann map and then define a map from the disk to the disk, which consists on just following this diagram, right? This you can prove it's an inner function. You can prove that basically it has some extension to the boundary, maybe in the sense of, for almost every point, in the sense of radial limits, but you can study this extension. But just be careful, this tells you a lot of things about the interior dynamics, because conjugacies really preserve dynamics, as you know, but be careful because if the degree is infinite, for example, this may not extend continuously to the boundary. And if the topology of the boundary is really ugly, the Riemann map may not extend to the boundary. So, you know, this is useful for what it is. And it's actually a whole field of study to see how these things transfer, maybe more in the sense of ergodic theory, from the boundary dynamics to the boundary dynamics. However, the interior dynamics, by the way, if the degree of F is finite, then this is a Blaschke product, and that's much better understood. And in any case, finite or not, we have the Denjoy-Wolf theorem that, as you know, tells you everything that can happen for a holomorphic map from the disk to the disk. It tells you in particular that there is a special point P in the closure for which all the iterates converge to this for all Pz in the disk, right? Or G is an automorphism, one of the two, right? So this basically gives you three cases. The case where P is inside and everything converges to P. The case where P is in the boundary, sorry for my disk that is not very round, and everything converges to the boundary. Or we are in the case of an automorphism, and then basically what you have is a rotation about a certain point. And just working a little, because this doesn't transfer immediately to the upper part of the diagram, but working a little, you get the famous classification theorem, which basically tells you that periodic components can only be basins of attraction, right, when the Denjoy-Wolf point is inside, parabolic basins when the Denjoy-Wolf point is in the boundary. This has a subcase, because maybe this Denjoy-Wolf point on the boundary is an essential singularity, and then you get what's called a Baker domain, or you get single disks in the automorphic case, right? So this is basically what we know about the interior dynamics of parabolic components, of periodic components. And let me say that if you are interested in the boundary dynamics, so like what is the dynamical system restricted to the boundary, you should consult the work of Chatitsky and Zunic, right, for rational maps. And let me advertise the very good work of my student Anna Jouvet, who looked at the transcendental possibilities, and, you know, so this is in some of her papers that are appearing recently, right, or in the archive. So she's really working hard on studying this transfer from the inner function to the upper dynamics on the boundary, using all kinds of things like Pessin's theory and many others. Anyway, this was just a quick introduction, because what we are today dealing with is wandering domains. Wandering domains, as I said, they only exist for transcendental functions. They don't exist for rational map, and this is an example of a wandering domain, a pretty special one, I have to say, because it's like the domains are translations of each other, and there is a critical point, a zero of the derivative that is mapping. So it's kind of a morally a super attracting basin, and all the points are slowly approaching, no, fastly approaching the blue point, right? Just to give you an example of an explicit one. Because in general, let me say that they are not easy to construct, okay? So they are not associated to periodic orbits. So it's not so easy to find examples of wandering domains. They don't exist for rational maps, you know that. They are only known since the 80s. Fatou and Julia didn't know if they existed, right? And also, they don't exist for every, or they cannot exist for every transcendental map. You really need singularities of the inverse to be infinite, right? So it's kind of a very general class of functions. And because they are so unknown, because they have been not so studied, because they have much more freedom than periodic components, I have to say that nowadays, many major open questions relate to wandering domains, right? There's more and more people interested in these, also for many other reasons that I will talk at the end, but because, you know, quasi-conformal deformations of a map are well understood when they are supported on periodic components, but not on wandering domains, and this has consequences for parameter space, etc. So somehow we want to understand the dynamics inside, we want to understand the dynamics on the boundary, and also the relation with the singular values. And today we will not do any of this, but we will do like a little bit, okay? We've been working on this for a while, and here I leave you some references about it. And slowly we are kind of figuring out everything that is possible, and even more interested, everything that is not possible for it to happen, right? So the first question, and that's why I mentioned before inner functions, is there also a relation with inner functions? So one can ask, well, one can see that yes, except that now you don't relate to a single inner function, but you relate to a sequence of inner functions, right? So given a base point, choose a base point on your domain and start iterating, Z1, its image, etc., Zn. And now choose your Riemann maps so that they map this orbit to 0. Okay, for example, this is one possible normalization. This will give you, but now observe, since the wandering domains are different, the Riemann maps are different, right? So you really get different inner functions at every step. So you have a sequence of inner functions. We call it one possible sequence associated to your wandering orbit. Clearly, other choices are possible. However, the properties, many interesting properties, do not depend on the choice of this orbit and or the normalization. And in such a case, we say also that this sequence of maps on simply connected domains is conformally equivalent to this sequence of inner functions. Okay, so yes, there is relation with inner functions, but now we leave the world of autonomous dynamics and we go more to the world of non-autonomous dynamics, right? So these are different sequences of maps. Okay, so one question you may ask is whether every sequence, oh, I think I missed one slide. Well, it doesn't matter. So one could ask if every sequence of inner functions, if every inner function can be realized as the inner function associated to a periodic component. That's the slide I missed. And that has been looked at in an interesting paper of Lacerrempe and Vaso in 2020 called Fatou's Associates. But also the same question can be asked here. Can every sequence of inner functions be realized by the wandering orbit of some entire map, right? And the answer, which is the one that we will answer today, under some conditions, the answer is yes, okay? Under some conditions that are exactly the requirement, and this is the theorem I will discuss today, the requirement of uniform hyperbolicity. So if you have a sequence of Blaschke products of finite degree, right, and they are uniformly hyperbolic, which I will define in my next slide, then I claim that there is an entire function with an orbit of simply connected wandering domains, such that my prescribed Blaschke sequence is the associated Blaschke sequence for my wandering domain. So in other words, that this diagram takes place for some entire map F and my prescribed Blaschke products down here, okay? And this is the realizability theorem, which we can do for under this condition of uniform hyperbolicity, which I will tell you in a second what it is. Here it is. So when I talk about Blaschke products, I will always consider the ones that fix 0. So they are, and also those that have degree at least 2. So at least I have one of these Mobius terms. And I'm going to ask as part of the definition that the degree of this sequence is uniformly bounded. So we have one of these guys for every n. So these coefficients depend on n, and this degree depend on n. So I'm asking that these degrees are uniformly bounded by some d. And I'm asking also that they are all of degree larger than 2. And then uniform hyperbolicity can be written in several ways. One is, for example, that all the zeros for every n and for every k are in a fixed disk smaller than 1. Or equivalently, that all the critical points of each of these maps are in a fixed disk independent of n also. Or equivalently, and this is less dependent on the domain itself, that given any orbit that I choose, I have a bounded hyperbolic distance from the orbit to the critical point of the map at that disk. So of the critical map, the critical points of Bn, okay? So these things are equivalent. And also let me remark that because of some easy hyperbolic property, if this happens for one orbit, it has to happen for all orbits, okay? So basically what we are asking is that the critical points and the orbits stay close together. Nobody is converging to the boundary, okay? Just because they fix 0, orbits converge to 0 naturally. So this is telling you that the critical point shouldn't accumulate on the boundary, exactly as the second property tells you, okay? In any of these cases, we will say that my sequence of Blaschke products is uniformly hyperbolic, okay? So they all contract, and they contract somehow in a uniform rate. Moreover, if this is true, we all can believe then that that when I choose this R or this S, take the maximum of the two, if I take the disk, so this is the disk, right? If I consider the disk of radius R, simply because of Schwarzschild lemma, this one will go compactly, the image will go compactly contained on the next disk of radius R. And what it says here is that consequently, when I take the pre-image of this disk of radius R, I'm going to get here a curve that contains the disk of radius R. This annulus, which I'm going to call later on AN, has, because of this uniformity, has a bounded modulus from above and from below, okay? And many other interesting properties that we will probably use and maybe not write, I don't know. But you can imagine that these kind of maps, the whole sequence works nicely with some uniform bounds because of this uniform R and S that are in the definition. Okay, so we will prove this realizability theorem using a surgery construction, okay? Why am I using surgery? Well, because I want, for my applications, for the applications we were interested in, it was important for us to keep control on the resulting entire function, okay? We wanted to know which kind of function we were obtaining at the end. I have to say, and I'm happy to say, that recently, Basso and David Martí and Lacerrempe announced a very general realizability theorem like the one I wrote, much more general than the one I wrote. So without this uniform hyperbolicity condition. So also for finite degree, etc. And some conditions are appropriate, but they use approximation theory. They basically say that any Blaschke product can be realized, right? Any sequence of Blaschke products, but there is absolutely no information whatsoever on what function can realize these kind of sequences. So this is one of the reasons why we didn't want to use this technique, okay? Second, because it's interesting in itself. I like to do surgery, so I like to do these kind of things. And I think doing surgery in an infinite number of domains at once has its own challenges. Okay, so let me, to start with, before we go to the more to the actual proof, I would like to show you how doing surgery in a finite number of the domains is easy, quotes, okay? So that that the problem is with the infinitely many of them and with the uniformity, and with the well, yes, the fact that there are infinitely many. So let me just show you how you would modify a little bit your function and do it with all kinds of freedom. Okay, and this has been done before. We did it with Christian Henriksen in 2009. And in this paper I mentioned a while ago of Vaso and Lasse and David, they also do exactly the construction that I'm going to use to show you. Okay, so let me just show you how to modify one step in the wandering domain sequence. So let me see if I remember how to do this. One moment. I will just get this picture, I think. Yeah, probably. Okay, so I will do this by hand because it's like by picture, it's easier if I do it by hand. Let's hope it works. So imagine that you have a sequence of wandering domains like this. So F sends UN to UN plus 1, etc., etc. And let's, for a moment, let's assume that it's finite degree. Let's make it easy. I just want to show you that you have a lot of freedom when you only want to modify a finite number of steps. Let's say 1. So in this picture, right, and this is in total generality somehow. So imagine that F is a map with this wandering domain. And suppose, for example, that I want to modify my function on some piece on the inside, right? But although I could do it directly, ignoring this, I could do it directly on this level. Let me show you how to do it here so that it gives you a hint of what is it that we will do later on, except that we'll do it at all levels, right? But if you wanted to change this Blaschke associated function and put another one, and let's make it easy because I just want to send a message that there is no problem with the complex structure. So imagine that I had another Blaschke product, right? A desired new Blaschke product, okay, which would be, let's imagine, right? So that everything is finite degree, so that everything is really nice. And that, let's imagine that for outside of a certain disk, okay, so that outside of this disk, these two maps are conjugate, which is very common because it's just one step, and because this outside of the disk that contains all the critical points, etc., this is like a D-to-1 covering, okay? By the way, these two things, of course, have to have matching degrees. If not, there is no hope, right? So imagine that this is the case, so that you actually have a map that conjugates these two maps on the yellow, right? But not necessarily on the inside. So basically what I want to say is that you could use this diagram to glue. So this map here, let me put here the identity. So extend this quasi-conformally to the interior, right? Imagine you had a conjugacy that was nice enough so that you can extend it nicely here. This is like a preview of what we will do, maybe a little more carefully. Here, I just want to give you an idea. And then this map here could be used as the gluing map. Gluing because I'm going to modify my F, and I'm going to define the new map, right, which is F hat, let's say, which equals F everywhere except on the pre-image. So except on this set over here, my modification region, if you want to say it, right? And in here, what I'm going to use is psi n composed with my new Blaschke product and with psi n plus 1. Okay, I could actually do this in U, and it would be the same because of the condition of UN. Because of the conditions I put, this would keep F on UN minus B. Okay, but anyway, let's just understand that I'm only modifying my function inside this domain. So, and in a way that it matches, in a way that the resulting function is quasi-regular. So this is a quasi-regular map. Okay, if I've done it carefully and it really coincides on the boundary, etc., etc., this is a quasi-regular map, and therefore I can try to make it holomorphic by integrating the structure that I'm going to define now. So define an F hat invariant Beltrami coefficient, or almost complex structure, as you want to call it, right? Which in this case, it would be, for example, so here is where I want you to pay attention. I can do it several ways, but one possible way is to say that on UN, I'm going to define the pullback of the standard complex structure. So in other words, I'm going to put here a field of circles, so the mu equals 0 complex structure, and I'm going to pull back by F hat. This is the same, actually, this is exactly the same as if I would put here, if I would do psi n star of mu 0. Okay, so this is coincides because of the as pulling back by this map up there, and the same here. And now notice, by construction, and then mu 0 everywhere else. Sorry, excuse me. So here I've put it, and I want you to observe that just this step is already forward invariant. This is the beauty of doing it just in one step, because now, because these maps are holomorphic, right? These circles are preserved in the whole forward orbit of my domain. And now what I need to do is to spread by the dynamics, what we call spread using the dynamics, to make a full mu defined almost everywhere on the complex plane using the dynamics, so that I have it F invariant. What does that mean? It just means that if I have a point Z, which after k iterates, for example, falls into UN, I will use this Fk, which by the way, it's holomorphic, to pull back the mu that I already defined here. And I just will pull it back to the infinitesimal, to the tangent space on Z of F at Z, so that this is done for every pre-image, k pre-image of my UN. So at any point, including this is for k equals 1. So here I will pull back by F and define my field of ellipses here and here, etc., but also on all the pre-images of these domains, right? So this really gives me an invariant complex structure everywhere except at points which never interact with the orbit of wandering domain. So I'm going to put 0 for all. So I'm going to put 0 on everywhere else, elsewhere. So this thing here is for some k. If for some k this happens, then I pull back by F to the k. If I never fall into UN, I leave U0. Notice that this is first of all, bounded dilatation, and second of all, F invariant by construction. And the bounded dilatation comes simply because all the pullbacks, except the first one, is done by holomorphic maps. Okay, so the dilatation does not increase. Okay, so if I can do this, then if I have an almost complex structure, a Beltrami coefficient, which is F invariant and of bounded dilatation, I can integrate. So my next step would be to integrate, apply the measurable Riemann mapping theorem, and that would give me a map from the plane to the plane, which would integrate, right, my complex structure, which is like it solves the Beltrami equation, right? And then the magic of dynamics with surgery occurs. On the one hand, you have your map F hat, which preserved the complex structure mu. On the other hand, you have your phi, which integrates this complex structure, right? So if I apply phi at both sides, the composition map, which I define to be phi minus 1 F hat phi, this is a holomorphic map. This is a holomorphic map, which I can picture as the top level of this diagram, right? So in here, I will have like my big F, which is the result of conjugating F hat with my phi, so that since this is a quasi-conformal homeomorphism, I will have now some other wandering domains, but the dynamics will be exactly the same. And my F will map one to the other. But attention, the magic is that this composition from here to, this composition from here to here is now holomorphic because I've integrated my structure, and Weil's lemma tells me that this is a holomorphic, conformal map. So really my associated, and same here, my new associated Blaschke product is the one I prescribed to start with, okay? So this is a bit of a messy example, but this is really to see that because we only did it at one step, really the complex structure could be whatever. This is actually at the heart of Sullivan's proof of non-existence of wandering domains, okay? It's the idea that, well, not really at the heart, but almost. The idea that forward, we don't have to worry, okay? And backwards, the pulling back takes care of all the invariants that we need. Okay, this is a much harder surgery than he does, in the sense that here we've cut and paste. We've really redefined our map. This is not a deformation. This is a new map that we've built. But as you see, we've realized an entire function with this new Blaschke product at one of its steps in the wandering domain sequence. And this is really the philosophy of what we are going to do, except that we have to do it at every end and at every step, at every horizontal level of the diagram. So the steps will be basically the same ones. So the first step will be constructing the gluing map, right? So we need to build this psi that we've used here, right? This map psi that we've built, we need to do it in general, okay? So we need to, Exactly. So first we need to build the gluing maps. So what do we need? We need to say, if I have, and we'll do it at the level of the disk, exactly as we did before. If I have two uniformly hyperbolic sequences, I want them to be quasi-conformally equivalent. So I want to find a uniform constant K and some maps from the disk to the disk that make this diagram commute. So that, careful, that they make this diagram commute near the boundary. Of course, this will not be possible in general, but near the boundary, I want that this diagram works so that if I'm near the boundary, and I'll be a little more precise, well, exactly here in those annuli that we drew at the beginning, I want this diagram to commute. So going by Bn should be the same as going the other way, right? And moreover, I'm going to require, and this will be important, that my quasi-conformal maps are the identity on this uniform disk of radius r. So this is the first step, and once we have the gluing map, then the rest will follow. This is really where the estimates take place. And let me just sketch how you would do it. which is really the quasi part of my talk somehow. 1 second. So this would be here, okay? So I have a sequence of maps Bn, and I have a sequence of maps Bn tilde, and I want to build these quasi-conformal maps, right? Which are, which I want to say that so I want them to commute with this diagram. I want it to commute at least when I'm nearby the boundary. What do I mean by this? Well, let's build this nearby the boundary. So do this trick, what we said at the beginning, take the pre-image of the disk of radius r in your previous domain. So this will give you some annuli, right? These maps here. And here you have a different one, which maps because you have a different map. And here you have another one, which maps to the next one, etc. And the same here, although maybe they are, well, for sure they will be different. Okay, these ones map to the red circle at every step. Okay, now start defining the map. So inside my disk of radius r, I want to put the identity. That's easy, right? So Hn will be the identity on the blue circles. Now I will define this H on the orange circles. How? So my Hn, let me write it here, will be the identity on the R. And now on the boundary, this is, by the way, my, so the next step will be to define it. Sorry. On these annuli, the purple annuli, which are what I called before the annuli Rn. An, sorry. So this is An. Okay, this is An minus 1. Okay, and on the boundary of these annulus, so on the boundary of An, what I will do is to go by Bn and to return by Bn tilde minus 1. So I take a point on this curve, I just map to the boundary of the R disk, I come down by the identity, and I go back by the inverse of this map. And yes, I have Bn inverses, but I either look at this as a lift or I simply choose one of the inverses and then define the rest by continuity. So this can be done, right? So observe that doing it like this, right? Every one of these purple disks, so this would define my function. So it's the identity inside, and this would define my function Hn on the purple disks. Sorry, on the boundary of the disks, commuting, making the diagram commute on these orange boundaries. Because now what I'm going to do is and here is the step where you need to do some estimates. You need to define an extension. So you have the identity on this boundary, and you have what we proved to be a quasi-symmetric map from the orange to the orange. And what we are going to do is to fill it up quasi-conformally. So psi n on An, interpolating Hn restricted to this boundary of An that we just defined and the identity. Okay, this can be done K quasi-conformally, independent of N. This is where the estimates are. Okay, so you need to make some uniform bounds on the moduli, that's kind of easy, but also on which kind of quasi-circles you get here. So the quasi-symmetric constant H that builds these quasi-circles, you need to show that there is one independent of the value of N. Okay, and we use some theorems on extension of maps on the boundary of annuli to the interior, but some quantitative estimates so that really you know what the constants that you get depend on, okay? And finally, once you have it on your purple, then the rest, you are interested in getting a conjugacy, remember? So you use the conjugacy. So you actually build it that way. So give me a point now on the pre-image of this purple annulus, right? So in this purple annulus, I will map by Bn minus 1 to my purple annulus. I will go back by the map that I already defined, and I will go back here. So basically, I will use the, so define extend to this remaining part, layer by layer, extend to Cn, right? Using the functional equation. So using that, you want Bn composed with Hn plus 1 to be equal to Hn composed with Bn tilde. Okay, so you actually build it so that on the yellow annulus, this is really conjugating the diagram. Okay. Okay, so that's how you prove. Well, of course, I'm hiding under the carpet all the estimates that are here, but this is important that this is independent of n. So actually, it only depends on R and D, the maximum degree of the maps, and the R that basically contains all the critical points and zeros. Okay, so this was the gluing map, because now what's left is very similar to what we already did. So what's left is to say, okay, now I built this quasi-conformal map at the disk level. No? So let me go back 1 second to this picture here. This is really at this level. It's just that now instead of 2 of them, we had like infinitely many of them, right? But remember that when we glued, when we changed our map at the wandering domain level, we used precisely this function to modify the map. So this is exactly the next step now, right? So gluing the new sequence inside an actual wandering domain. So if you have an entire function, you start with an entire function which has a simply connected orbit of wandering domains. You give me a prescribed sequence of Blaschke products, and what I claim is that, so uniformly hyperbolic, of course. Suppose actually that both sequences are uniformly hyperbolic, and you may complain rightly that I didn't define what this means here, but you can define it in the natural way, which is using this distance from orbits, the hyperbolic distance. Then I claim that you can actually glue in, you can replace the inside of your wandering domains to plug in your prescribed Blaschke sequence. So there is a sequence of conformal maps that makes the diagram commute, so that really your new map is the associated Blaschke sequence. And the nice thing is that since you are only going to modify the map inside the wandering domains, your old F and your new F are going to be conjugate, so they are going to do exactly the same as they did outside of the orbit of wandering domains. And in fact, beyond, like in the yellow region, they are also still be the same, okay? And this is my last picture, but this time I will be a little faster, or I don't want to take too much time, right? So the replacement surgery, I think you can all believe now that this is going to work, but let me just very quickly sketch it. So this was to go a little faster, right? So start with your function that has your wandering domain. These BNs are the natural associated Blaschke sequence. So these are the Riemann maps. And these are the new guys that we want to plug in. And these are our gluing maps. Well, the gluing map will be the composition, but these are our quasi-conformal maps that we just built, right? Which conjugate. So this diagram commutes perfectly, all of it, in the yellow regions. So outside of this part here. And remember, these HNs are also super nice inside the disks. So here is the identity. So I'm not doing anything. Okay. So now I do exactly what I did before, only that I do it all at once. So this will be my actual gluing map, psi n minus 1, psi n, etc. Quasi-conformal, right? So I will redefine. So let me call U the union of all the domains, just to make it easier. And I will just redefine my map as I did before, and I'll say leave F as it is on C minus UN, on C minus U. And then on each of the UNs, you just glue, right? So you do psi n, then you do your new Blaschke product and come back. And believe me that, well, believe me, you can check that by construction, this really equals F on the yellow. Let me just write it like this. So really, this is a modification only inside the orange angles. Because of the conjugacy that we built inside HN, on the outside here, I'm doing nothing. Okay, I'm just gluing in a nice way inside. And this is really good because now, well, just observe that this is uniformly K-square quasi-regular. Okay, why? Because this works, so doing 25 iterates, it's going down once, doing 25 iterates here and going up. So it's twice K quasi-conformal, but only twice. And therefore, we can do exactly the same trick as before. So we can define at once a complex structure, which means pull back the standard complex structure down here and pull it back by your quasi-conformal gluing map, all at once. Okay, all at once. And then, so this is on UN. This is naturally forward invariant by construction, spread as we did exactly before by the dynamics. But the beauty here, okay, and then again by the measurable Riemann mapping theorem, obtain a integrating map, and then your new map, phi f hat phi minus 1, which again will be able to put on the top level, right, will have the properties that we want. So here will be my new F, and this map from top to bottom will be conformal. So again, the associated Blaschke sequence to my new function is exactly my prescribed Bn tilde. Let me just make a couple of comments of why this works, right? This works, well, it works because it's clear from the diagram that it works, but it made me think a lot of why this works, right? And it's this, really this foliation. An alternative way to define this complex structure would have been to put the standard complex structure in the red disk and pull back all at once. So you put the standard on all the red disks, which remember, they are invariant, so one goes inside the other, so we would be fine by holomorphic maps, because inside this disk we have we have a holomorphic function. And now when you start pulling back, at the first step it only goes to this annulus, at the next step it goes to the second level annulus, at the next step it goes to the third level annulus, so that the annuli are kind of having these joint orbits. So this structure never steps on itself, okay? You need to make some pictures to see this, but it's kind of magic in the moment. the reason is because we are doing all this on the region where it's a covering. Another thing that can convince you is the fact that orbits pass through the complicated annulus, the orange to blue, once and only once. So give me a point, it will be yellow, yellow, yellow until it falls in this annulus, and then next it goes inside the disk forever. So really you step on the quasi-conformal region of your map once and only once, okay? Anyway, this is the way to do it, and the only thing that is a bit left is to say, okay, how do you find this F which you use as a template to glue in the rest? And this is some results of ourselves some time ago, which basically tell you that you are very free to choose Blaschke sequences of any degrees, and those are realizable. I'm not going to get into it. The funny thing or ironic thing is that this is proved by approximation theory. So then what control do we have in this function? None. But for the case that we need it in our applications, which is that all the degrees are uniformly equal to D, then in fact this template function can be found explicitly, okay? So that in this dn equals d case, which is the one we actually use, we really have a lot of control on the function. And let me just finish, sorry that maybe I was a bit too long, but I want to finish with some comments. So I would like to finish saying how I started, saying that this work is really motivated on the quasi-conformal deformations of entire functions. So how to change your complex structure so that at the end, you get a function QC conjugate to your original one. The ones that are supported on wandering domains, which are very little understood up to this moment. The way to study this is using the framework of McMullen-Sullivan, or also what we generalized for entire maps in 2009 with Christian Henriksen. And to apply this framework, it's very important to make to classify your Fatou components or subsets of these Fatou components into places where your grand orbit relation, which means the grand orbit, backwards, forwards, everybody related to you, which is kind of an equivalence relation, whether this is discrete or indiscrete. Because when you study Teichmuller space, you can split the study of your Teichmuller space into these completely invariant subsets. So for periodic components, every type of periodic component belongs either to the discrete set or to the indiscrete set. Well, it turns out that for wandering domains, this is not the case. And in fact, the behavior is very opposite, so that we can construct an example where discrete and indiscrete grand orbit relations coexist. Okay, and this was really the goal of our work, to see that wandering domains are more complicated, one has to be a little more careful. And the way we construct this example is using the construction that I just gave you before, okay? Which is by building a sequence of Blaschke products with this property and then gluing it into an actual wandering sequence of an entire function. In particular, we do it for a fixed degree, and that's why we can really be happy with having a template that we can understand. So the control on the final map really allows us to prove this coexistence, which was our main goal. But anyway, all of this will be a matter of another talk. And thank you very much for your attention. Here you have some wandering domains to have a look at. Thank you.
All right, so let's thank Núria. And let me open the discussion. So are there any comments or questions?
I can start. Well, first of all, thank you for both Núria and Han for wonderful talks. I enjoyed them. Núria, so I mean, you mentioned this result of Lasse Rempe and his collaborators, right? They also do something similar, but they don't assume. You said they don't assume uniformity, or
no. So I don't know, this is not published, it's only announced, so it's not even in my archive. I just heard a talk about it. So I cannot give you a precise statement, but my feeling is that basically they take compact sets, disjoint compact sets going to infinity, and some holomorphic map defined on a neighborhood of this compact set. Okay? In particular, you could take disks, copies of disks, and Blaschke products because they all extend to a neighborhood, right? And under these conditions, they are able to build an entire function which which has a wandering domain. Well, these compact sets need to be regular. Well, they need some conditions. And because it's from compact set to compact set, these maps have to have finite degree, okay? And I don't know if there are any other conditions, but nothing like this hyperbolicity, this is clear. And then by using approximation theory, they claim that they can get an entire function which in every wandering domain, in the closure of the wandering domain, you have these equivalents to the actual compact set maps, okay? So that my diagram, the one I drew, would really work up to the boundary even, because it really, they get this conjugacy on the closure. This is pretty impressive. It's very nice, and I think it tells you all the things that can happen. But again, this map could be horrible, right? So no information as usual when you do these Runge type theorems. No information on what kind of function, infinitely many singular values, who knows? In particular, for our construction, we needed a strong control on we needed to make sure that no singular value from outside would ever fall into our wandering sequence, right? And there is absolutely no hope of any of that in approximation theory. Did I answer your question?
Yes, thank you. So there's another question. So I was, recently worked with Misha Lubich and Sabia Mukherjee and Dimitrius and Russell Lodge and so there are many other papers. And we did something similar for like replacement dynamics on some wandering components, but not that was just for rational dynamics. So no worries about this. We were replacing basically we were replacing like Blaschke products by some kind of reflection group actions.
Okay.
We were gluing in reflection groups. For us, the maps there were actually anti-rational maps, but it doesn't really matter. So like if you take index 2 subgroup of a reflection group, then you're fine. You have orientation perturbed maps and stuff like this. So instead of basically gluing in prescribed Blaschke product, what we were doing in the case of rational maps, we were gluing in like reflection groups there in like ideal triangles or polyhedra generally.
Okay.
And the surgery we used is actually we needed to use not a quasi-conformal surgery, but David surgery. Yes. So I mean, it's an interesting question whether under your assumptions one can also replace it with instead of like prescribed Blaschke products, you can replace it with some kind of reflection groups, maybe because you have uniformity on like on your map F that you constructed, it has uniformity on the components. Maybe you can also prescribe, like you can sort of choose to prescribe. Sometimes you prescribe maybe Blaschke products, sometimes you prescribe like reflection group.
Well, I think the difference and the interest maybe, this is like the difference between what I showed and what's usually done when you actually replace a piece of a map, blah, 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 is that here you have to do it at infinitely many places at once. So you are like in the non-autonomous world. So on the one hand, it seems that it makes it easier. On the other hand, the fact of having infinitely many, you have to really be careful with the pullbacks of the structures, because unless you know something about what you're gluing in, it's very easy that that you cannot make it invariant because you cannot get a definition. But what you say is very interesting. Whether you could glue reflection groups inside wandering domains, I have no idea.
Yeah, I mean, absolutely. Yeah, I understand, absolutely. So you have to be really careful, especially when you replace hyperbolic dynamics by parabolic dynamics, and you have David.
Let me just
David,
Let me
differential, you have
Yeah.
to have some kind of like separability condition, like uniform separation or something like that, to solve the equation.
Let me say that it would be super interesting, I think, so what McMullen does is that he can replace whole Fatou components. Okay, so if you have something that is quasi-symmetrically conjugate on the ideal boundary, even if your boundary is awful, he has this beautiful surgery where he glues in a whole new map up to the boundary. Notice that I've done it very safely on the interior, right? So he can do it really up to the boundary. The problem, we tried this was our dream, right? But to control the constants in that setting, we were not able to do it. It's an interesting question whether somebody could do this under some conditions, maybe, I don't know. And then you would be very free to do a little more, I guess.
Thank you.
So actually, can I ask a question that goes in a similar direction as what Sergey said? Namely, if by using these David type quasi-conformal maps, could one maybe relax this uniform hyperbolicity condition that you had?
Well, it's not unthinkable. It's really not unthinkable because, well, I don't know, as long as some uniformity you need, right? Some. It's only that maybe you can relax it, that it's not so interior, so that you can go closer to the boundary. So maybe you could put some rates at which you allow the critical points to approach the boundary. I'm sure that you can do better. We did what we needed to do, and also because it was like the first example where we did this globally and uniformly, so we were happy with it. But clearly, if you just look at the surgery problem, there is room to improve, I'm sure.